At 11:17 p.m. Pacific Daylight Time, on the 1st of June, 1966, a surveyor spacecraft set down on the face of the moon. 35 minutes later, its television camera transmitted the free world's first close-up of the lunar landscape to the Earth tracking station at Goldstone, California, 231,000 miles away. With this event, the United States reached another milestone in its lunar research program, first operational flight of the Centaur. The operational Centaur flies a direct descent, single-burn mission, its engines firing only once. The two-burn Centaur is in development. This vehicle will first propel its payload into a low parking orbit. Engines then shut down, and the Centaur coasts until it reaches a new launch point. Engines then fire a second time to thrust the payload into the planned trajectory. AC-8 is the first of two Centaurs assigned as flight test vehicles in the two-burn mission development program. Engines are uprated for higher specific impulse. AC-8 also carries the improved inertial guidance system. There are two other significant differences between this and the operational single-burn version. The attitude control and vernier engines are uprated and now include 14 thrusters in place of the original 6. At the forward end, the balanced thrust system to evenly distribute the thrust of venting gases in opposite directions during the coast phase period. These systems required an extensive test effort before the Centaur could be committed to flight. Centaur's main flight components operate at a temperature around 423 degrees below 0 Fahrenheit. To obtain valid results, testing must be conducted at this temperature. This is Convair's Liquid Hydrogen Test Center at Sycamore Site B, effectively isolated 15 miles north of the main plant. The key cryogenic fluid, liquid hydrogen, flows from the 13,000-gallon storage tank through vacuum-jacketed lines to a number of test pads. Other tanks and lines provide liquid nitrogen, gaseous nitrogen, high-pressure helium, and central purge vacuum. The vibration pad is a multi-purpose, flexible work area. The arrangement of lines, valves, heat exchangers, and tanks blends the gases and liquids to deliver temperature and pressure-controlled vapor to the plug-in outlets. A unique feature of this pad is its mobile vibration system capable of driving vibration exciters up to 12,000 force-pounds. Vibration testing with liquid hydrogen, costing about 50 cents a gallon, provides a significant cost reduction. Previously, this was done with less dangerous liquid helium at a cost of $11 per gallon. The cost saving on a single test can amount to several $1,000s. The mobile vibration equipment is housed in two trailers. At the left, a trailer containing a matching transformer and heat exchanger for the vibration exciter. Behind the blockhouse is the control equipment trailer. This holds a typical array of recording equipment and consoles used to generate commands and document test events. For random vibration, a 40-channel equalizer analyzer shapes the desired frequencies and analyzes the vibration input to the specimen. Part of the adjacent bank of instruments generates a sine sweep vibration pattern. Either of these, random or sine sweep, can control the vibrator, or the signals can be mixed. The blockhouse commands the operation of 3 pads. It includes remote-controlled television and multiple recording channels. In a typical operation here, engineers ran design-proof tests on a disconnect joint, part of the Centaur balanced vent system. The elbow attaches to the Centaur nose fairing, which jettisons in flight. The opposite end remains with the flight vehicle. The tent over the pad provides a controlled light environment for engineering photography. Strobe lights synchronize with the vibrator and camera shutter to provide high-speed, slip-sync motion pictures for later evaluation. For the test, hydrogen vapor flows through the specimen. The shaker, to which one half of the specimen is attached, will program through increasing sine sweep vibration up to 2,000 cycles per second. A second run adds random vibration, followed by a mechanical disconnect of the joint. Then engineers repeat the vibration in the Y and Z axes. Then the specimen is reversed and the tests are run again. This cold shakedown of a critical part verified its structural and functional integrity. One of the continuous operations at Site B involves stress analysis of space vehicle materials. This dog bone sample has been cut from one of the rolls of steel from which the Atlas and Centaur are produced. On this one, two sections have been joined by a spot weld test pattern. The technician checks the welds for porosity by applying a penetrant dye to one side and developer to the other. For cold testing, the middle of the sample passes through a sealed chamber. This assembly is submerged in a liquid nitrogen bath and the ends of the dog bone attached to hydraulic stretchers. Liquid hydrogen flows through the sealed chamber, chilling the stainless steel to its flight temperature. The sample gets up to 50,000 pounds of stretch, or cycles between two selected tensile forces until it fails or exceeds a programmed number of cycles. This is a transparent booth which is used to hold a captive atmosphere for simulating flight enclosures. Inside is a Teflon cylinder which carries venting gas from Centaur's liquid oxygen tank to the vent port. Instruments measure temperatures, flow, motion, and disconnect loads. In this test, cold nitrogen gas flows through the cylinder while mechanical arms cycle it. When Centaur separates from Atlas, the Teflon cylinder disconnects. The test qualified the unit for flight. Roughly in the center of Site B, a 100 cubic foot insulated tank provides a capability for cold flow testing over long time periods. This is one of two similar tanks on which is mounted a Centaur hydrogen vent valve. This valve cycled for a total of 150 hours. The same fixture provides rapid boil-off rates for high-flow venting, as in this one, a 50-hour test. At the far corner of the site, an earth revetment isolates one pad from the rest of the facility. This area supports hazardous testing, such as any requiring the use of explosives, or which may abruptly release a large cloud of hydrogen gas. The vertical panel and fin are part of the Centaur nose fairing and vent stack through which hydrogen vapors flow. The tests simulated launch disconnect from the facility vent line. Instrumentation included high-speed motion picture cameras and, in the blockhouse, a television videotape recorder for immediate review after each test. Early tests were at ambient temperature. The final series utilized a housing around the disconnect purged with nitrogen gas to allow observers to detect any nitrogen ice formed at the super cold disconnect. The recorded data verified a properly functioning system, establishing confidence in the design. Spaceflight is a challenge to man-made materials and to the engineer's creative imagination. Research such as this is necessary to prove and improve the products of design. The test towers located at Point Loma provide a proving ground for the larger units or systems of the Centaur vehicle. For example, many of the components seen in the Site B sequence are units of the balanced thrust vent system. For this system, engineers were concerned with the temperature environment in Centaur's forward compartment, which would result from the flow of hydrogen vapor through the toroidal duct. They installed more than 130 thermocouples to measure temperatures on electronic equipment packages and of the atmosphere around the packages. Beneath the tower, large heat exchangers convert liquid nitrogen to gas, which provides an inert, temperature-controlled atmosphere within the nose fairing enclosure. The test simulated a launch pad chill-down and flight sequence. Engineers were also concerned with pressure buildup within the tank and system, since Centaur does not vent during launch and early flight. In the early tests, the expansion bellows exposed to the atmosphere of the compartment produced an overall temperature which was 100 to 200 degrees too cold. As a result, the nitrogen gas changed phase, liquefied, and dripped onto electronic packages. This was corrected by designing an insulation cover for the exposed bellows. In subsequent tests, the balanced vent system performed within requirements and qualified for flight. At G-Tower, engineers completed tests of the hydrogen peroxide engines. These include turbines which pump liquid oxygen and liquid hydrogen to the main engines and jets which control Centaur's attitude in space. The blockhouse programmer simulated the on-off commands which the guidance system produces in flight. The miniature thrusters control Centaur during the coast phase and also provide a small amount of acceleration to keep propellants at the aft end of tanks ready for pumping to the main engines. In these runs, all elements of the system performed satisfactorily. This fixture simulates the umbilical booms at Cape Kennedy's Complex 36. The arms support lines which attach to Centaur prior to launch. During an early attempt to launch AC-8, an umbilical connector did not release properly, scrubbing the flight. Engineers restaged the event here to isolate the problem. Repeated runs indicated reliable performance of the system, obtaining data which established a high degree of confidence in the components. The tests removed a constraint on the flight. This is the 2,000-pound fairing which shields Surveyor during its flight through Earth atmosphere. It jettisons about 200 seconds after launch. One of the K-Tower test operations simulated this event. At jettison, a shape-charred system cuts the ring which attaches the fairing to Centaur. Thruster bottles inside the nose cap force the two halves away from the vehicle, and they swing out and away from the flight path. To avoid damage to the fairing, two bumpers on the tower absorb the thrust force as fairing halves swing out. The Centaur test vehicle was in flight condition, tanked with liquid hydrogen and liquid nitrogen. After an aborted first attempt, the final test resulted in a clean separation, proper thrust, and precise tracking. With the completion of this task, the Point Loma crew began to prepare for another K-Tower test, which would measure and determine the maximum loads which Centaur can support. This effort will support NASA's planning for possible advanced missions with Centaur. This is Sycamore Canyon Stand 4, the site for full-scale hot-firing tests of Centaur's liquid hydrogen engines. Here, hot-firing tests evaluated engine sequencing for both first and second burn. In addition, engineers conducted a thorough analysis of propellant tank modifications. The two-burn development program included 4 cold flow cycles and a total of 15 hot firings. The final activity at S4 evaluated the engine gimbaling system. Thrust chambers were gimbaled individually and together under ambient conditions through a range of frequencies and displacement arcs. With completion of these tests, Sycamore S4 was closed, ending a 4-year period of service in research and development of liquid hydrogen technology. This is the Atlas booster for AC-8. one of two vehicles assigned to support development of the two-burn Centaur. Airlift to the Cape was from Miramar Naval Air Station in San Diego. At the Eastern Test Range, preparation for flight began with the mating of Atlas to its launch pad, Complex 36B. After preliminary checkout, the Convair crew secured the adapter section, then hoisted NASA's high-energy Centaur stage into position. The spacecraft for AC-8 was a mass model made to duplicate the weight distribution and center of gravity of Surveyor. This is the final building block of the total space vehicle. In preparation for the mission, engineers exercise all systems, then put the vehicle through a simulated countdown, launch, and dummy flight. April 1966. AC-8 lifted from the pad 2 minutes after 8 p.m. Eastern Standard Time. It turned from its launch pad heading of 115 degrees to a flight heading of 103 degrees, then began a gradual pitch over into its shallow flight angle. The vehicle reached Mach 1 58.5 seconds into the flight, encountered maximum aerodynamic pressures 18 seconds later. The most efficient use of energy for this flight called for booster cutoff and jettison at the point where the vehicle reaches an acceleration of 5.7 Gs. This occurred at 142.36 seconds, close to nominal, 36 miles high, and 45 miles downrange. "34 seconds later, insulation panels jettisoned. A few seconds later, the nose fairing jettisoned. During booster flight, the Atlas sustainer was burning a fuel-rich mixture, resulting in depletion and cutoff 7 seconds early. Cause of the fuel-rich burn is not determined. However, the guidance system computed the error and later compensated for it by commanding an additional 8.5 seconds of engine time during the Centaur first burn. First burn placed Centaur into a 90 nautical mile orbit. This was the most significant period of the test, during which an important objective was successfully achieved, providing for the first time a method of controlling the behavior of the high-energy propellants over a full 25 minutes of zero-gravity coast. From telemetry data, Convair's computer produced this visual display of propellant utilization. The dots represent sensors in the tank. These disappear as the liquid level drops during the first burn. Real time is compressed into a few seconds. The data provided valuable information on propellant behavior during coast phase. After first burn, propellants were quickly settled and maintained proper position, as calm as a mill pond throughout coast phase. However, the supply of hydrogen peroxide was depleted, possibly due to a leak in the system. At start of the second burn, the propellant boost pumps, powered by this fuel, started but immediately began to slow down, presumably from lack of hydrogen peroxide. The main engines fired, but decayed in thrust because of propellant starvation due to loss of pumping power. Centaur released its payload 37.5 minutes after launch, but short of the required mission velocity. The two objects went into orbit ranging between 96 and 188 nautical miles. Even with the loss of hydrogen peroxide, the AC-8 flight was considered one of the most significant and successful of the Centaur program, achieving a notable breakthrough in space flight. The balanced thrust vent system performed well within expectations. Attitude was extremely stable throughout. Information obtained will be applied to the flight of AC-9, the second vehicle for two-burn research and development, scheduled for launch during the last quarter of 1966. This is Surveyor 1, first of the spacecraft assigned to land on the moon. Before a space mission launch, the Atlas, Centaur, and Surveyor come together for the first time at NASA's Combined Systems Test Facility in San Diego. Hughes Aircraft builds the Surveyor, and a crew from its Culver City plant followed the spacecraft to San Diego to perform a systems readiness test. Combining of all stages which make up a space mission ensures early confidence in the interaction of all systems. This was theoretically the first moon flight, only simulated and without propellants. Surveyor will be mated twice more at Cape Kennedy before the flight.
Propellant.
Cape Kennedy, Florida, Memorial Day, 1966.
Pressurization.
The scheduled date for the final performance of Atlas 290D and Centaur 1D.
Centaur autopilot.
To intersect its target on the moon, Surveyor SC-1 must lift from the pad within an aperture in time between 9:40 and 10:27 a.m. Eastern Standard Time.
All recorders fast.
Minus 12 seconds.
Engine start.
Minus 5, 4, 3, 2, 1.
Launch time was 9:41, 1 minute into the time aperture. Atlas rolled from its launch pad heading of 105 degrees to a flight azimuth of 102.285 degrees, then began its pitchover into the trajectory. All powered flight events were close to nominal. Atlas, Centaur, Surveyor 1 was to become a storybook mission with a smooth transition through every step. Centaur's final maneuver was a turnabout in space. Hydrogen peroxide jets added a vertical vector to put Centaur out of a direct line with the spacecraft. Unused propellants gassed out in the direction of flight to widen the gap between the vehicle and spacecraft. 5 hours later, the distance between Surveyor and Centaur was 1,054 kilometers, about 3 times greater than the required 336 kilometers. After launch, control of the mission passed to the NASA Center in Pasadena, California. The Jet Propulsion Laboratory commanded the mission through its Deep Space Tracking Station at Goldstone, California. 63 hours and 36 minutes after launch, at 11:17 p.m. Pacific Daylight Time, Surveyor made a perfect 3-point soft landing on the moon. 35 minutes later, Surveyor transmitted its first picture from the moon, a 200-line television still photograph which viewed one of the landing pads. Later, the camera transmitted 600-line pictures with finer definition. This was an early shot looking down at landing leg number 2, and clearly shows a deformation of the surface caused by the impact of landing. During its active life, Surveyor transmitted 10,338 pictures over the 12 Earth Day period of operation. Then the lunar night enveloped the spacecraft, and Surveyor went into a frozen sleep. It was expected that the frigid 260 degrees below zero would put electronic systems out of commission, but they survived to transmit again for a short time. The National Aeronautics and Space Administration has scheduled the second operational flight for September with Atlas Centaur 7, Surveyor 2. The Centaur stage left San Diego for the Cape on June 24th. The present schedule includes 10 Centaur operational missions. Beyond this, there are 14 advanced missions which have been proposed. These range from Earth orbit missions to solar system exploration, extending from orbit of the Sun to Mars, Venus, Jupiter, and Saturn.